Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Arun Venkataraman from the University of Massachusetts in Amherst. I've known Arun now for a few years, and I've had the privilege of working with him on a couple of interesting projects as well. So before Arun graduated, he was at UT Austin, where he did work on background TCP transfers, which I believe now have made their way into some ideas, at least in a couple of IBM's products about background transfers. And since then, he's had a stellar record, including 2 NSDI Best Paper Awards, like in consecutive years, and gone on to do some interesting stuff. Today, he's going to describe some of his recent work on block switching networks. Yeah.
Thanks, Ratul, for the introduction. I'm not sure if the microphone is active, but I assume you can all hear me. So let me first of all apologize for starting late. So my excuse is that I spent the last over an hour in a cab. I thought I knew Seattle traffic and thought 40 minutes would be enough to come from Seattle, but it turns out he took the wrong exit, and then we pulled out the GPS, and I was helping him figure out his GPS to get here. So there. Okay, my talk today is about block switching. The title is Towards a Robust Protocol Stack for Diverse Wireless Networks. Much of the work in the talk is based on an NSDI 2009 paper this year. This work, all the work that I'll talk about is in collaboration with Ming Lee and Devesh Agarwal, students who did the HOP work, faculty at UMass Deepak Ganesan, and then students Aruna Balasubramaniam and Shajung Tai, who are doing some of the more open-ended and exploratory stuff that I'm going to touch upon at the end of this talk. Okay, so what's the motivation for this? There's a big gap today between what's advertised as the max capacity of a wireless technology and what applications actually get. So this is an example. I'll describe our test bed itself in more detail, but these are experiments conducted from our test bed. We chose 3 different links, 1 good link, 1 average link, and 1 bad link. And we simply measured the good put achieved by UDP and TCP over these links. So UDP is a lower bound on what you can achieve. This is an 802.11b network, but similar results can be observed for G and N as well. So UDP places, yes?
Are you only looking over 802.11, or are you looking over other wireless?
Much of this talk is only going to be about 802.11, but to the extent possible, I'm going to give the motivational arguments and justify HOP's design with minimum recourse to 802.11's deficiency, as little as possible, and focus more on TCP's fundamental problems over wireless. Okay, but HOP itself is designed for 802.11 as it is. Okay, so UDP places a lower bound. You can at least get as much as what UDP can get, but what most applications which use TCP see is the TCP throughput, which shaves off a huge factor. What's particularly noteworthy is that on bad links, and that's not like the worst link, that's somewhere in the bottom third or bottom quartile of the links, there's a big order of magnitude, or almost 2 orders of magnitude of a difference between what you can get, or what you should reasonably expect, and what TCP gets.
So what is bad? Bad is
high loss rate links.
That's high loss rate, bad RSSI, or is it this congestion?
High loss rate as observed by UDP.
No, is it due to poor RSSI or congestion there?
There is no congestion in this. These are experiments done when just the channel itself. So poor RSSI is the main reason. Attenuation, whatever, to the extent multipath exists in the building. This is a building test bed. Okay. So feel free to interrupt me with questions. It's a very small audience, and the more interactive the talk, the better. It's all very simple stuff that I'm going to talk about. Okay. So why does TCP perform so badly over 802.11? I will go into these. I'll describe some fundamental problems, not just with TCP, but sort of the TCP IP stack itself, the fundamental assumptions that are embodied in this architecture, in this layering of functionality in the TCP IP stack. So the first fundamental problem is the use of end-to-end techniques in wireless transport. What do I mean by end-to-end? End-to-end means that the transport treats the network as a black box. That is, the network does not explicitly assist transport in its objectives. So I'm calling them as end-to-end techniques. So the first problem with end-to-end techniques is that of rate control. Rate control is fundamental to TCP, but rate control is problematic when in wireless environments for two reasons. One, the environment itself is fluctuating a lot. So TCP behavior is completely defined by the loss rate, or the loss and the delay signals observed by each packet. But these fluctuate a lot, and TCP performance degrades with this fluctuation. The second is it's hard to even distinguish between what losses are caused due to congestion and what losses are caused due to other effects like channel effects or interference-like effects. So these are well-known problems with rate control over wireless networks. These have been studied for over a decade. Okay, the second fundamental, the second problem with end-to-end techniques in wireless is one with retransmissions. End-to-end retransmissions are wasteful. For reliable transport, for end-to-end reliability, you need end-to-end retransmissions. But then what end-to-end retransmissions do is, if a packet goes, say, 2 hops into the network and then gets dropped because, let's say, 802.11 gave up, or a node crashed, or because of whatever reason, then you're going to retransmit the packet along the whole way, right? But you could, ideally, you could have retransmitted it just from the point P all the way up to the destination. We don't do this because packets are small, they're harmless, we just retransmit them. Right? But these overheads catch up over time. The final problem is the very assumption, yes?
The retransmission point actually is, there is a lot of link layer retransmission. So end-to-end, and the thing is with end-to-end retransmissions, it's there as a safety mechanism that I'm guessing nobody would argue for taking it away. So I guess what you're probably arguing for is a different balance between like link layer retransmission and end-to-end. So 7 retransmissions, for instance, is not enough.
Correct. We don't know how to set this number exactly. You could make this 100, and then there are problems with that. You could make this 1 or 2, there are problems with that. We don't know where to set this number to. There are problems with each setting.
Sure. So, actually, I don't know. Has people looked into for a single wireless hop, just doing adaptive link layer retransmissions?
Right. So this is not an easy problem because when you say adaptive, presumably the number of retransmissions on each link changes according to some network-wide objective. And this, as far as I know, is not an easy problem, and I don't know of people trying to do this for link layer retransmissions. What's done in practice commonly is that people accept that TCP is great. It's the universal transport protocol, and therefore by itself, without link layer retransmissions, it's going to suck terribly in wireless, and so we're just going to make the wireless environment good enough for TCP to work as is over wireless. And so they just pick a number like 10 or 11 in typical implementations. Setting it to a really high value doesn't help because you're going to end up underutilizing resources. You're going to end up doing retransmissions and bad links too much. And setting it to a low value obviously is not enough because then TCP performance will suck. Okay. So the third problem with end-to-end techniques is the very assumption that an end-to-end route exists between the source and destination. This may not be the case in mobile ad hoc networks or an extreme point in the design space, which is disruption-tolerant networks or DTNs. In fact, this whole protocol, HOP, is primarily designed with mesh networks or WLANs in mind, but then it's inspired by DTNs. By looking at an extreme point in the design space, by looking at what works when there is no route available ever between the source and destination. That is, the network is always partitioned. By looking at what works there, we're able to come back to mesh networks and get significant performance improvements even in well-connected mesh environments. Right, so this is a reason to look at DTNs, not just because they're interesting as Windsurf would have it for interplanetary communication, but for real benefits in real environments. Okay. The second fundamental problem with wireless transport today is the high overhead associated with treating a packet as a unit of control. Right? So what do I mean by this? A packet is a unit of control or reliability at the link level. Right? So ARQ is per packet. Channel access is per packet. So you're paying some overhead for all of this. And yes, 802.11 is designed to keep these overheads low, but let's just look at 802.11 as an example and see how these overheads catch up. Right? Channel access overhead is non-trivial. You have to wait until you get access to the channel. There's a diffs overhead, and then if the contiguous segment of diffs sensing doesn't go through, you back off, and then you try again. And then there may or may not be an RTS or CTS overhead per packet, depending on how you've configured your network. So this is significant channel access overhead. The second is LinkLate IRQ. LinkLate IRQ is necessary to make TCP work as is, like in wired networks on wireless networks. But then ARQ introduces its own overhead. Every time a packet transmission fails, you're going to back off for increasing amounts of time and then try again. This increases the overhead per packet. These overheads are not trivial. I'll show you some numbers. These add up to like 60% or to 2x of an overhead in real environments under load. Actually, both with and without load, sorry. Okay, the third fundamental problem with wireless transport is the complex cross-layer interaction that it introduces. So as an example, I'll show you many examples of such cross-layer interaction through this talk, but the simplest example is that of TCP rate control with the variability in round-trip time introduced because of LinkLate IRQ. Every time a packet transmission fails, you're going to again sense carrier, back off, and try again. And you will keep backing off exponentially. How much you back off depends on the implementation specific details, but then it introduces a significant amount of variability. You can tune TCP retransmission timeout estimates to specific environments, but there's only so much room there to play with. I mean, you can't do much better than TCP once you take that approach. Right? So this kind of a cross-layer interaction is a fundamental problem. ARQ is an example, bitrate control is wireless bitrate control is another example. You're doing rate control at two different levels, and they interact negatively. Okay, so that's the motivation for why we need to think from a clean slate perspective about wireless transport. I'll next show you a protocol, HOP, first its design, and then experimental evaluation over a mesh test bed we have at UMass in the computer science building. And then I'll present some higher level arguments for why the key idea in HOP, which is switching blocks or big chunks of data as opposed to small packets, has fundamental benefits for the design of a network protocol stack that's robust across a variety of different wireless environments. Okay, so key ideas in HOP. So HOP is a clean slate redesign of wireless transport. The three key ideas basically build upon the three motivational points I introduced. End-to-end problems with end-to-end techniques, treating packets as a unit of control, and then complex cross-layer interaction. So the solution for the problems with end-to-end techniques is to go to a hop-by-hop transport protocol. You don't have end-to-end rate control anymore. You have hop-by-hop congestion control, which I'll show is significantly more robust than end-to-end rate control. To deal with the second problem, packets as a unit of control, that's where the key idea of blocks comes in. What is a block? A block is simply a contiguous segment of data. Just think of it as a big packet at a high level, but the difference is that it's not a big link layer frame. It's a bunch of packets over which the overhead of ARQ and channel access gets amortized. So you're sending these packets in a block in a burst mode. That's what amortizes the overhead. And this overhead is significant, is one of the important points in this talk. To address complex cross-layer interaction, for the lack of a better word, I'm going to call this minimalism. We try to remove redundant functionality across layers, like ARQ redundantly at the link layer, at the transport layer, rate control at the link layer, at the transport layer. So try to minimize this to the extent possible. Okay, so HOP consists of 5 main components. The bottom part are the per hop or single components that give you single hop performance benefits. The top 2 components give you performance benefit over multi-hop networks. The most fundamental component of HOP is this building block that I'll call a per hop reliable block transfer. So reliably take one block, transfer it to the next hop along the route. Right? Here's where you get most of the benefits of aggregation or blocks as opposed to packets. So end-to-end for a protocol to have end-to-end reliability, it's not enough to just do per hop reliability. You need some end-to-end acknowledgements as well. This hop accomplishes using a novel scheme called virtual retransmission. Any reliable transport protocol must do congestion control, otherwise it will just be inefficient. It will underutilize network capacity. But instead of doing TCP-style AIMD end-to-end rate control, we do back pressure. Back pressure has some very attractive properties. It's been well studied, and it's much more robust because it's a hop-by-hop congestion control scheme, and it obviates the problem of rate estimation. I'll show you how it does that. These two components are per hop components. The ACK withholding component is a scheme that comes for free with the basic design of hop itself and gives us significant savings in the presence of hidden terminals. If you're blasting blocks without carrier sense, a huge chunk of data without doing carrier sense, in 802.11-like environments, you're going to exacerbate the hidden terminal problem. And ACK withholding is a simple solution that sort of is more or less overhead free. The last component is for delays, right? It's great to show significant throughput benefits for bulk transfer, but TCP is TCP because it's universal. It works for SSH, SMS, and what have you. And HOP achieves these delay benefits by doing prioritization based on the block sizes. Yes?
So you're using back pressure, which is great, but your stated goal was to reduce complexity and make this more minimum. Back pressure requires signaling. You just drop packets. That is an implicit signal. So that's sort of in contrast to your stated goal of making this a minimalist protocol. A minimalist protocol won't have end-to-end signaling.
Good point. I don't have a good defense for that. As I said, for the lack of a better term, I'm using the word minimalism. What I intended there was to remove redundant functionality to the extent possible and minimize interaction across layers. So wireless bit rate control, TCP rate control. ARQ at the link layer, reliability at the TCP layer. So these control loops at two different layers interact negatively, and that's the intention. Try to remove as many features as possible. If you're going to do it at a higher level, then just do it at the higher level and don't worry about doing it at the lower level. Yes, back pressure introduces some signaling, but I'll show you that this signaling it gives you significant benefits even in a single hop network. The signaling overhead is really, really small, and that's one of the contributions of this work, making the signaling overhead negligible, because back pressure as an idea has been around for almost 2 decades now, but the big stumbling block is to translate those throughput optimality properties that reside on paper to a practical implementation, and this is one such effort, and there are other such efforts, recent efforts trying to do the same. Okay, so let's begin with the most basic building block of HOP, the per hop reliable block transfer component. The mechanism has 2 key ideas, burst mode and a block-based ARQ scheme. Burst mode just means that you send a batch of frames as a burst without doing carrier sense in between, so without the channel access overhead in between. We call this a TX op or a transmit opportunity. This exists in 802.11 standard 802.11 implementations. In fact, in more recent 802.11 standards like N, it's particularly optimized for this kind of a burst mode transfer. The second idea of a block-based ARQ scheme amortizes the overhead of ARQ by spreading it over a batch of packets inside a block, as opposed to paying that overhead for each frame. Yes?
Are you getting rid of fate sharing between various parts of the same block? Especially the block that you at least one of the frames will go away, right? Or it might be, there's already partial packet recovery kind of schemes where you say that the larger the packet size, there are parts of the packet that are already well received, but it's only a few parts of the things that drop off. So you're just going to make the fate sharing a little bit even wider, because your entire block has a very low probability of getting moved.
You're saying we'll exacerbate the fate sharing problem by going to blocks. You also said something about partial packet recovery. Let me say that partial packet recovery techniques are orthogonal and can reside underneath a protocol like HOP. Much of HOP's design is at the link layer or above. So pick whatever frame size you want, make the link as good as you like using whatever techniques under the link layer you like, and then we will reduce the overhead using HOP compared to the combination of 802.11 and TCP. And as for the fate sharing point, it is true that wireless losses are often bursty, that if one packet gets lost, it's quite likely that the high loss rate will remain for some time, or the channel effects will remain for some time. It's hard to quantify that other than experimentally, and I'll show you that. It gives you significant improvements.
Confusion in your question, I think. Once a packet in a block is lost, only that packet is transmitted, not the entire block.
Maybe it'll become
actually
clear when I tell you the bitmap, when I just go into this bitmap protocol.
But there is an interesting question related to what you're saying, which is if your link layer is so efficient because it's using partial packet recovery or it's using symbol level transmission or something like that, that you're losing the least possible amount of data. That you still need all these schemes on top. Right? Where is the line? Right?
Good question. I don't know the answer. We won't know until we experiment with those underneath Hop and see how much benefit you get out of that and how much benefit you get out of this. One thing I would like to point out is the most significant benefits in Hop come under high load. And so link level techniques will make a single link really good. But then under high load, TCP has some very fundamental problems that Hop addresses. So that's orthogonal to optimizations that you introduced below a link. Hop can incorporate that.
So beyond packet corruption, you need backpressure.
Right. Backpressure gives you benefits at the network and transport layer, and it's complementary to optimizations underneath the link.
Basically, you don't want to transmit more on the path than the path can handle.
Yeah.
How should I think about the trade-off of doing burst mode where I have perhaps a bunch of smaller packets being transmitted back to back versus simply extending the maximum packet size?
Very good question. I'll touch upon this a little bit more towards the end. In Hop, we use just standard frames, 1,500 byte frames throughout our experiments. It's not a good idea to increase this frame size too much because then you're exponentially increasing the likelihood of at least one bit getting corrupted in the packet.
Partial packet recovery.
Right.
You've got
Sure.
some other
Exactly.
technique
Right.
at a lower layer.
Right. So you can use. I'll touch upon this. I'll tell you how these techniques can be incorporated underneath Hop as well. Right. So if you do extend what a frame is, then you need to have sort of more error correcting information inside it. And with that, you can have smaller frames. So again, you can have, inside a block, you can have smaller frames. The point here is the channel access and ARQ-like overheads that you pay, instead of paying it over something that's the size of one packet, pay it over a much larger chunk of data.
Part of the reason I was asking was because one of the overheads you didn't mention is the packet preamble, which is actually pretty substantial when you're sending small data packets.
Right.
This could potentially reduce that.
Right. Why don't we keep this question on the stack, and we'll come back to it at the end. Okay. So what is the block transfer, the basic per hop reliable block transfer itself? It starts with a handshake. There's a send packet. There's an acknowledgement packet. The send says, the send is a request to send a block of packets. An example of a maximum block size is 1 megabyte. That's the default implementation in Hop. The ACK tells the sender what packets or what frames in that block have already been received. So it's a bitmap. So the sender only has to send the remaining packets. So this is a multi-round protocol. So in every round, there's a SYN ACK, B SYN B ACK handshake. The B just stands for block. After the handshake, the transmission itself proceeds through a bunch of transmission opportunities or TXOPs. Each TXOP in 802.11 A, B, and G, the implementation allows for about 6 to 8 frames without carrier sense. But there is carrier sense in between TXOPs. We had to do this because we didn't have access to N, which allows sort of a whole frame, a really big jumbo frame to go without any carrier sense in between. But this is how we implement it on ABG networks. So there's a CSMA overhead. There's a TXOP that's about 6 to 8 frames, and then there's a CSMA overhead between any two TXOPs. But the control overhead, there's no reliability in between. There's no ARQ. There's a SYN ACK and then 1 megabyte of data with carrier sensing once every TXOP, which is once every 6 to 8 typical sized frames.
Also allows burst out.
This is 11E.
Oh, okay. Easier to teach you.
Right. So 11E basically gives you these W optimizations called the WMM optimizations. We use some of those, both the prioritization optimizations as well as these TXOPs. The protocol itself is not, or the modulation rates are not fundamentally different from ABGs. So I'm grouping them together. Okay. So that's it. I mean, this is at the heart of Hop. This is the building block. There's no rate control here. There's no ARQ here. Or sorry, there's no per packet ARQ here, right? The goal is still to transmit the block reliably over multiple rounds of these BSYN BAC handshakes and bursts. Okay. So per hop reliability, not enough for end-to-end reliability. Hop uses a novel retransmission scheme called virtual retransmissions. That again is possible because these blocks are big. You can afford to spend more overhead on big blocks. Having designed the per hop reliable block transfer protocol itself, or component of hop itself, virtual retransmission actually comes for free. The idea here is to leverage in-network caching. So if a block has gone multiple hops into the network and for whatever reason does not make it further, let's say because of a node crash, right? The destination in this case is D, then you want to retransmit it from the point B. And to do this, basically what hop does is when there is a timeout at the source, the timeout is simply just a moving average of previously observed round trip times for blocks. It doesn't have to be robust. Any simple estimate is good enough. At the timeout, a special BSYN packet with it's special because there's a virtual retransmission flag set in the BSYN packet. You get back a BAX saying, oh, I already have the packet because B already has the packet. When B tries this with E doesn't have the packet. So you only retransmit the packet over the parts of the route that have changed. So if this is a relatively static network like our mesh network, then retransmission overheads and the wasteful end-to-end retransmissions are significantly alleviated by this. Yes?
I remember your complexity point, and I keep worrying that if you're waiting for an entire block to get across, or you're waiting for things like let me reroute, or aren't you making it more variable for the upper layer? The upper layer is trying to do anything reactive to what it sees.
The upper layer is the application here because we are at the transport layer. What are the metrics? Let's look at what metrics are important to applications. These are throughput and delay, right? Throughput for large files, delay for small files, and those are the metrics we'll evaluate. So it's a good question. Let's wait for the experiments.
What about jitters?
We will look at that too. We will look at sort of the effect on VoIP traffic. Yes?
How many blocks are in flight typically?
How many blocks are in flight? This will become clear when I introduce the back pressure component, which is next. There's one block buffered at each node. That's the default implementation in Hop, and I'll tell you sort of what role that level of buffering plays in this protocol. Okay, and finally, there is an end-to-end acknowledgement because we want end-to-end reliability in this protocol. So that's it for end-to-end reliability. Any reliable transfer protocol must have congestion control. If you try using UDP under load, the utilization of the network would simply collapse. So Hop uses back pressure to do this. The mechanism is simply to limit the number of outstanding blocks for each flow at a forwarder. So in this example, the number of outstanding blocks is limited to 2. So the source, let's say, sends these blocks. There's a slow link. The last link is slow between D and E. This will lead to buffering at the last but one hop. At this point, because the limit is 2, in this example the limit is 2, D will stop accepting any more blocks from its previous hop. And so the BSYNs will keep getting retransmitted at coarse grain intervals, but then the BAC will not be sent. So there's no extra overhead in doing this. This is just the per hop reliable transport protocol. Or there's minimal extra overhead in implementing back pressure itself. And similarly, this back pressure will propagate all the way back up to the source. Okay? So that's the basic back pressure mechanism. Why is this useful? Back pressure can give you significant benefits in throughput. Right? In fact, back pressure is most interesting. All the theoretical work on back pressure tells you that it can give you optimal throughput in a network, and I'll define in a little bit what that means later on the talk. But this is an example for why it can significantly increase utilization in the network. So the bottleneck here is the 10 Mbps link, and all the other links are 20 Mbps except for that one link, which is a bad link, the 1 Mbps link between F and G. And so if you didn't do anything at all, the blue packets, the blue flow, which is the top flow, and the red flow, which is the bottom flow, they'll keep sending packets. And the effective throughput is going to be 6 Mbps because this flow is bottlenecked by the 1 Mbps link. This flow because it shares this link equally with the other flow, gets only 5 Mbps, and you'll just have infinite buffering at F. You could drop those packets, which means you'll have to retransmit them. That leads to wasted work. Right? So it's clear here why we need to bound the amount of buffering. If we bound the amount of buffering to a small value, let's say in this example 1, which is the default implementation in hop, then this is what will happen. Blue packets will keep going through the top link. There'll be 1 packet of buffering at each hop, and then the blue packets will get all of the 10 Mbps. So the aggregate utilization in this case is 10 Mbps. Right? TCP tries to get similar utilization benefits. The difference between what TCP does and what back pressure does is TCP will simply back off end to end because it will notice that there's a bottleneck link of 1 Mbps. Whereas back pressure is doing this in a hop by hop manner. TCP does rate estimation. Back pressure does not do any estimation. It simply it's flow control at each hop. It says you can send now versus you cannot send now. So there's no rate estimation problem like the one that AIMD tries to solve.
Well, it seems to take a slightly simplistic view of TCP. I mean, it's not really rate control. I mean, it is ACK-based automatic. So there's no explicit rate estimation going on in TCP. You basically send when ACKs come back. So,
right.
in some sense, there is an end-to-end back pressure there that if your packets are not making it or it's really slow because it's ACK-based, it has the same effect. But you're right in the sense that effect is kind of like back pressure, but it is end-to-end. Right? And by the notion that when you create that effect on a per hop basis, there are benefits to that. But those benefits are not related to explicit or implicit rate estimation because those two properties are somewhat similar, it seems.
The difference between the way TCP tries to do and back pressure tries to do is TCP tries to do this rate estimation by translating it to a window estimation problem. So AIMD tells you when to halve the window or when to increase the window, whereas back pressure does not have such drastic changes.
I think Ratu is simply pointing out that TCP also has a flow control mechanism. Essentially, you can't
end-to-end flow control.
Right. So basically, if your window is full, you can't send until ACKs come back, and that automatically means an end-to-end back pressure.
Correct. So the difference is between end-to-end versus hop by hop. Hop by hop makes it more robust because you're aggregating all the fluctuation and noise in estimation over many links if you're trying to do this end-to-end.
So there is a IEEE standard that does hop-to-hop back pressure for large Ethernet deployments inside data centers.
Large what?
Ethernet networks inside data centers. And they have all sorts of problems you have to worry about because if you apply hop by hop back pressure, you sometimes end up doing unnecessary freight share. So if your flow is going, you end up doing unnecessary freight share. Mm-hmm. So if you apply back pressure on the entire link, not on the per flow basis, then you're basically blocking off all the flows that are going through their switch. Mm-hmm. Some of which may not be either contributing to the bottleneck or their bottleneck might be someplace else.
This is header line blocking.
Something like that.
Right. So there's many. So back pressure as a concept simply refers to feedback that's propagating at each hop about how fast you should send or how often you should send, right? There's many different ways of implementing this. In fact, the way we implement it in hop is not how classical back pressure works. ATM tried to do it in a different way. There's many different implementations. We do it per flow, and you're right. If you don't do it per flow, there's head-of-the-line blocking issues. We do it per flow in hop, which means you actually maintain flow state. Yes. This is a wireless network, and yes, again, this contradicts, as I'm surprised no one pointed out that how can you call this minimalist if you're maintaining state inside the network, which is why I will not dwell so much on the minimalist point, but we do it per flow because we're not worried about scalability in a wireless network so much as we are in the internet. Yes?
There's also the point that nobody really limits you from opening 100 flows or sending the same amount of data. So per flow or anything that tries to put per flow failures is clearly vulnerable to gaming, right? For example,
yes.
The red flow just starts like
correct.
Spinning itself twice and it'll kill the blue.
All of hop's design is assuming.
You're assuming the equal amount of pressure is applied to each of the network and
That's what he says. Back pressure is
yeah, back pressure is per flow, but that means we'll get 100 times back pressure if you have 100 flows.
right. I will get 100 times back pressure, but the other guy will get more back pressure because I'm taking 99.
So Shrikant, the short answer is that we assume senders are honest. If you try to game it, both TCP and hop have their own different sets of problems. We don't address any of those here. Our goal is sort of performance in a benign environment first. Okay. Excuse me. So the next component is ACK withholding. The benefit here is that it significantly mitigates the hidden terminal problem. And again, like back pressure and virtual retransmission, the overhead comes for free once you have designed this per hop reliable transport protocol. The idea is somewhat similar to RTS and CTS, except RTS and CTS have their own problems. This is the reason why RTS and CTS is typically not turned on in production networks, because they have a high overhead. The per packet overhead is high. It's also conservative. That is, it prevents some transmissions that could have happened. Right? The way ACK withholding happens is, as the word says, the receiver at each hop simply withholds the ACK. You send a BSIN. You don't send a BACK if there's multiple senders sending you BSINs. So you don't send multiple BACKs out. This addresses the common case of single receiver hidden terminals, a classic 3-node hidden terminal problem. So A and B both try to send a BSIN in this example. C receives both of them. Let's say it successfully receives both of them, so the BSINs themselves haven't collided in this example. It's going to withhold one of the BACKs, send A the BACK, but hold B's BACK. Let A go first, and then let B go next. Right? That's it. So the BSIN and BACK are playing roles somewhat similar to RTS and CTS, except this is not conservative, and the overhead comes for free and is amortized over a huge block of packets. Yes?
Say in the sequence you described, nothing prevents B from sending a BSIN, right?
Correct.
Which would mean it would keep sending BSIN.
Correct.
Which can cause collisions.
Correct. BSIN is a small packet, and it's sent at coarse grain intervals. So if a BSIN fails, you have a timeout, and eventually you'll retransmit the BSIN. So you'll corrupt some frames in a concurrently transmitted block. Well, you'll corrupt one, maybe 2 frames.
Why don't you send a B hold back?
Good question. This comes up. I mean, we played with different designs. It didn't seem to reduce the overall signaling overhead or the chances of collisions again. At some point, you have to make a call of what you will send without trying to do an explicit channel access scheme there.
Seems somewhat simpler because C doesn't have to remember to send a B out. If it just immediately sends B hold, it becomes kind of stateless.
Right. The catch is B holds can also be lost. What I didn't tell you, what the paper tells you, what I didn't tell you in the talk is BSINs and BACKs are sent with ARQ turned on because these are more important than regular frames. So you try to make BSIN and BACK transmissions as reliable as you can, but they can still be lost, and so eventually you need a timeout at the BSIN, and you have to send the BSIN again because you don't know if your SIN was ever received by the receiver. So if you have that, yes, sending a B hold or a NAC message can help in some cases, but it didn't seem to help much in our experiments.
So logically, BSIN and BACK are synchronous. Now you have ARQs on them. So how do you set this is kind of detailed, how do you actually
Default ARQ.
set the timeout for BACK?
There is no timeout for BACK, there's a timeout for BSIN. So you send a BSIN, right. Normally you would get a BACK right away if everything is good, and if ACK withholding is not happening and back pressure is not happening. If not, the timeout, I believe it's set to something like a couple hundred milliseconds, but I don't remember the exact value. But it's a coarse grain timeout.
Can't you make the BACK act as the CTS? For example, if BACK actually has the identity of A, for example, then we can just go back for the data transfer.
It's possible to do that. Yes. Given that the per hop reliable block transfer needs a BACK to come before it can start sending the blocks, I mean, it's implicit. The BACK is there anyway. But in the specific example, you could get away with that optimization. There are other cases where it won't work. Okay. The last component is for reducing delays. delays for small transfers. This is done through just prioritization based on block sizes. There's two components to this: sender side prioritization and receiver side prioritization. So let's say an SSH traffic is competing with FTP traffic. SSH is sending 1 byte at a time. Well, it says 64 bytes here, but it could well be a byte. The sender, if the size of the block is less than a threshold, in our implementation this threshold is 16 kilobytes, the sender will simply send the data along with the BSIN. It doesn't wait for the BSIN BAC handshake. Okay. At the receiver side, the receiver simply prioritizes small blocks over large blocks. And so you keep the delays of small blocks, especially really, really small or single packet blocks, low. Right? Because now you have this explicit handshake, BSIN and BAC, you have this power at the receiver to make a decision, both at the sender and receiver, to make a decision of how to do this kind of a prioritization. So once you've defined the per hop reliable transport protocol, for a single link, all of this incurs very little overhead because the mechanism is in place already. With the simple optimization, hop gives you low delays both for large file transfers, effectively meaning high throughput, as well as low delays for small file transfers or even single packet transfers. Okay, so all of these ideas are extremely simple. You've probably encountered them in one way or the other at some place or the other. And this would not be interesting if we are not able to show significant improvements over TCP. And that's what took us almost 2 years to show consistent gains across a wide range of metrics over TCP for a lot of different workloads and environments. So that's our test bed. It's a 20-node test bed. It's the second floor of the CS building. It's a Mac Mini-based test bed. I'll show you experiments with B and G in this talk, mostly with B, some with G. The first experiment is comparing hop and TCP's throughput over a single link. So there's one flow, one link. No competing traffic, to the extent we can ensure that. So experiments were done in the night. The way this experiment is conducted is that we randomly sample, with repetition, links in our test bed. There are about 60 unique links that are active, that work at all in this test bed. Bitrate control is turned off. It's all set to the max bitrate, which is 11 Mbps in this case. And this shows a CDF of the good put across those links, achieved by hop and achieved by TCP. What this tells you is that hop achieves 60% better throughput on the median link compared to TCP in our test bed, and even less on good links. On good links, TCP is really good. The median improvement is about 60%, which comes from the per hop protocol. This is largely attributable to reducing channel access and IRQ overhead and not doing rate control. Right? There's no load effects here. What's particularly noteworthy is the bottom quartile links. Right? The first quartile benefit is 28x. In the first slide, I showed you like a 40x difference between UDP and TCP, and this is how hop bridges most of that gap. Yes?
Which TCP implementations do you use?
Right. So that's a good question. We to the extent possible, we try to pick the best variant of any protocol we are comparing against. Thanks for bringing this up. TCP here is also given the benefit of burst mode. So it's not like hop gets the benefit of turning off using TXOps. TCP also gets TXOps. TCP's ARQ is turned to the maximum possible limit. We set it to 100 on the card, but we noticed that the max only went up to 20 or so because of some implementation details in the firmware. And we found that setting the ARQ on a single TCP consistently improves by using TXOps because it reduces channel access overhead, and by setting ARQ limits to a high value. On a single link, it helps. On a multi-hop route, it helps simply because if a packet goes 2 or 3 hops and then gets stopped, it's more wasted work. So the more ARQ you give to TCP, the better links, the better route you present to TCP, the better TCP performs. So it has that benefit. Which variant of TCP? We tried using the best. I want to say this is cubic, but the details are in the paper.
Not the best for wireless networks. Cubic is if you want to push an enormous amount of data. Why not use Westwood?
We used Westwood. It actually performed about 10% worse consistently than the version used here. I'm not sure the version used here is cubic, but I can look that up in a second. Yeah, so there were different options available in Linux, and this is cubic, and cubic performed the best in our testbed. And Westwood is really designed to give you a lot of benefit in the case where you're going over a single hop wireless link and then going to the internet. This is not the environment. We're not worried about the internet here. Right? So it doesn't actually help us in this environment. Or we found it didn't help us. Yes?
So what are you transferring? What's the traffic?
Oh, good. The traffic here is just a long transfer. We're measuring the throughput over a big file. So these are most of the experiments are throughput experiments, unless I explicitly tell you it's being delay is the metric being quantified. Okay, so the second experiment is again a single flow experiment. There is no load effects here, but over multiple hops. So we randomly pick source destination pairs, and we only include source destination pairs that are at least 3 hops away. The hops, the routes are chosen by OLSR, by running OLSR before at the beginning of the experiment. Here we see, again, the first quartile and median benefits are significant and more than the single hop case, but the lower quartile is not as impressive. Right? This is basically because in this testbed, OLSR, we run a routing protocol. So unlike the previous experiment, which was a distribution over all links, all working links in the testbed, this is using only the good links. So the benefit of over TCP of hop is lower. Yes?
How many hops and how many of them are wireless?
At least 3 hops, and the number of paths is, I believe, 100 with repetition. So what's being chosen is a pair of nodes that are at least 3 hops away randomly. Okay, so let's take a more detailed look into this robustness behavior. What exactly is happening in this lower quartile? Why does TCP degrade? What happens to grace under pressure for TCP and hop? Right? So this is a very simple experiment where we modify the driver to drop a certain fraction of packets after 802.11 has happened, above 802.11, below TCP. What this shows you is that this shows you the good put as a function of the loss rate, single link, no interference, no load. Right? What this shows you is that at 20% loss rate, TCP throughput goes down to 0. This is not surprising. Right? This is expected. We all expect this to happen. The square root P relationship holds when the loss rates are small, but 10% loss rate is disastrous for TCP. Hop, interestingly, shows a near linear degradation, which is about the best you can expect. I mean, the 1 minus P factor is about the best you can expect if a loss rate of P is what the channel gives you. And so this is where most of the single link or single hop benefits of hop are coming from. No rate control, removing unnecessary overhead.
This is a very strange place in the stack where you induce loss, it seems.
Right.
Because you're not letting link layer recovery take over.
Correct. So the previous experiments actually showed you with link layer recovery. We also did some experiments where we tried to actually make links bad by causing interference, by using a jammer. I don't have those experiments right now, but this really brought out the point, just the transport level point, which is, imagine a link that, despite all of its optimizations, gives you a certain loss rate. How does transport behavior depend on that loss rate?
Yeah, I guess what I meant to suggest, I've never seen like a 10% loss rate at the transport layer is very uncommon.
Yeah. I mean, you have so much, like 2 retransmissions, 3 retransmissions, and a 50% loss rate is going to go down to link rate loss rate is going to go below 10.
Yes.
Right. So
that's for a single link. When you aggregate it over multiple links over a multi-hop path, those losses are going to exponentially aggregate.
So the jammer experiment, did it look like this, or did it not look like
There's
this?
a lot of variance in the jammer experiment. That's one of the reasons why we didn't include it in the paper. It doesn't show you as clear-cut a difference because it's hard to get the jammer to work correctly with hop and TCP. But it shows a significant, hop is significantly more robust than TCP with the jammer, yes.
So maybe you have another graph later on, but the question is, what's the impact on fairness?
Correct.
So,
The biggest numbers I'll present, which is, I guess, the next slide. This is all about fairness. This is where hop really shows its resilience over TCP, its performance and fairness improvement over TCP. So let me tell you first how this experiment is conducted. This is a load experiment. So we saw single flow, single hop, single flow, multi-hop, and this is multi-flow, multi-hop. 30 flows over multi-hop paths. And like before, it's plotting the CDF here is slightly different from the ones we saw before. This is a CDF of the 30 flows. So this is about the bottom 7th flow, and that's the 23rd flow. This is the 15th flow, right? So it's plotting the distribution of flows, all done at the same time. What this shows you is that the median flow in hop gets a 20x improvement in throughput and 2 orders of magnitude better throughput compared to TCP for the lower quartile. The purple line here, we included this line here as opposed to the previous ones because it gave more improvement. It performed better than TCP. This is the hop-by-hop version of TCP. It's more robust than TCP because instead of doing end-to-end rate control, it's stitching together a bunch of TCPs. And this is an idea that's been floating around for a while. It's a common optimization to make TCP rate control more robust. We implemented this, and interestingly, this implementation also gets some benefit of back pressure because the sockets at each hop effectively are doing flow control on each TCP. So it has some benefit of back pressure. So it does give you better improvement. It gives you about 4x of a median improvement than TCP. The number hop compared to TCP is actually 90x. Hop compared to the hop-by-hop TCP is 20x. So it gives you improvement, but it's not quite enough. There's still a lot of room for improving fairness, right? Why is this fairness? Because it's a distribution of flow throughputs. So the question to ask is what happens to the mean throughput or the aggregate throughput, the sum of the throughputs of all flows. Here it's very hard to beat TCP. This is where TCP's strengths are I haven't seen a protocol that can beat TCP, that has been shown to beat TCP under heavy load. This is very difficult to do. Hop gets a very slight improvement, 10 to 15% mean throughput improvement, which is not significant. And the reason is because TCP's rate control is very unfair. What it does, it kills off most of the flows in bad paths and lets a small number, actually 2 or 3 flows out of the 30, to go and blast at a high speed. And so its aggregate throughput remains high, but it's very unfair. Many of the flows get near 0 throughput. This is a log scale, the x-axis. Okay, questions? So this is the centerpiece graph. This is where hop shines really. So the improvement is the biggest numbers come as fairness gains, not as mean or aggregate throughput gains under heavy load. Yes.
Aggregate retransmissions, do you know if we had any analysis of that makes a difference?
Aggregate retransmissions?
Yes. Just on a if you added up all of the devices and how readily you get access. Is it showing the same type of fairness? I mean, I'm just trying to understand if I'll skip it. I'll check with you later.
Okay. So the performance breakdown. Hop has 5 different components. Which component gives you how much of a benefit? I'll show you the microblock prioritization separately because it impacts delay. But the main components in hop are really ACK withholding for hidden terminals and back pressure for congestion control. What this experiment shows is the good put for 3 different experiments. one with 10 concurrent flows, 20 concurrent flows, and 30 concurrent flows. So ACK withholding gives you 20% and 20%, and back pressure respectively give you 20% each, and they add up to a 40% improvement when the load is low. When the load is really high, so under low load they're both important, right? When the load is high, back pressure is a significant contributor. ACK withholding by itself gives you 2.5, back pressure by itself gives you 3.7. They both together give you 4.x improvement over the default hop. This is not TCP. This is a default hop with no congestion control and nothing for hidden terminals, right? The one thing I should mention is here, we also did UDP, of course, and variants of UDP as well. It's not worth showing UDP on this graph. I mean, it's just most flows get 0 throughput because a congestion collapse happens. So one lesson here is when you show load experiments, even with 3 to 5 flows, UDP is not the protocol to compare against. If you want to compare throughput under load, TCP is the protocol to compare against, and it's very hard to beat TCP under load. Okay. So under load, back pressure is the most important contributor. The experiments, all of them so far, were over this for a mesh-like environment. I'll show you next the benefits over a typical WLAN environment. Here, the experiment is that a bunch of senders are sending to a common AP. So you compare hop against TCP and TCP with RTS CTS turned on. So there are 7 senders here. 6 pairs form hidden terminals in this example. What you can see is hop's mean throughput is again not much more than TCP's mean throughput. TCP is unfair. The median is 244. Hop's median is 652 because it kills off most of the flows and lets 1 or 2 flows go ahead and blast. TCP with RTS CTS turned on reduces the mean throughput but makes it more fair, as expected. What happens with hidden terminals? Actually, TCP has an interesting solution, if you will, for hidden terminals. It'll just kill off some of the flows and very likely let just 1 flow go ahead. This is TCP's solution for hidden terminals. So the throughput remains high, but the fairness is affected. Low delay. Yes?
Question on the previous slide. How realistic is this AP deployment? How many APs do you have on this floor?
Oh, this experiment is just with 1 AP and 7 senders.
No, what I mean, say if I were deploying WLAN in this building, how many APs would I cover the floor with? Because
that's a good question.
The thing is, like,
there's more than one. There's a few on each floor that we have in the building.
In practice, whenever I've done measurements of like deployed WLANs, I find it really hard to actually come across hidden terminal scenarios because the AP density tends to be high. There used to be on different channels, so everybody's actually, in some sense, in the same contention domain in realistic deployments.
Right. So in our building, with the default transmit power levels, it's about 2 to 3 hops of a diameter going from this end to that end, because there's walls in between and whatever other environmental effects come into picture. And so hidden terminals, we actually checked that 6 pairs form hidden terminals, which is when they send simultaneously, the throughput is really, really small.
Right.
As opposed to
So what I meant to suggest, like if you actually do experiments with the realistic WLAN deployment, you will not see such a high fraction of hidden terminals among clients connected to the same AP, because clients that are far away are more likely to connect to different APs, and they also are likely, they're kind of like close enough but not far enough, they're also likely to be on different channels.
Mm-hmm.
So I think
we haven't experimented with those scenarios. So channel assignment as well as multi-AP settings, we haven't experimented with. Okay, small delays. So in this experiment, there's 1 small transfer competing with 4 large transfers. And the x-axis here is the size of the small transfer, the y-axis is the delay. The different bars are the delays. This is on a log scale. The red line is hop. Hop consistently achieves lower delays for all sizes than TCP. So delay is not being affected, and this is simply because of the microblock prioritization scheme. So the sender just sends it if it's less than 16 kilobytes, and then the receiver prioritizes small blocks over large blocks. Okay, So I'll skip a few of the other experiments. HOP is designed for reliable transport protocols, so we don't expect HOP to be used for VoIP traffic, but we did evaluate the impact of HOP because it's sending this burst of packets on VoIP. It turns out that HOP doesn't affect VoIP much. It affects VoIP quality slightly more than TCP, but it's not significant. And HOP's benefits, these are all A22B experiments, but over 11G also HOP's benefit remains the same. I will show you this experiment because it's relevant to the diverse networks theme. HOP is a hop by hop protocol. So if an end-to-end route is not available, HOP will continue to function. TCP will completely break down in a DTN environment. Right? So this is an experiment where we have 7 nodes. 2 and 4 cannot talk to each other without going through 3. Periodically, we just bring down 3, and then 5, and then 3, and then 5, and so on. So the network is always partitioned. 1 and 7 are always partitioned. So you need a disruption-tolerant protocol to accomplish transfer from 1 to 7 in this case. And HOP, with different levels of the back pressure threshold, gives you different levels of performance. Setting it to a higher value of buffering here gives you better performance because these nodes are down for a longer time. The comparison point is DTN, not TCP here, because TCP doesn't work and it's not designed for this environment. And DTN 2.5 is TCP based, so it uses TCP to transfer a file at each hop. So the benefits we see here are sort of commensurate to the single hop benefits we saw over TCP earlier. Right? What we need to do is to look at high route flux environments where not a simplistic experiment like this, and that's when we'll know if hop really gives you significant benefits when the network is in a lot of flux. What we did do is study network and LinkLate dynamics in the mesh test bed we have. So there's something interesting going on here. The red line again is hop, and we turn on OLSR, the routing protocol. Instead of fixing static routes, we keep it on. So OLSR is working, recomputing, adapting to load all the time. So there's all these cross-layer interactions with the routing protocol also going on now, as well as bitrate controls. So the bitrate control algorithm is just a sample rate algorithm that comes, that's the default on the MAD Wi-Fi drivers.
What link metric is OLSR using?
ETX. So interestingly, OLSR improves TCP fairness. And we don't quite understand why this is happening, and this sort of brings out why generally analyzing cross-layer interaction is difficult. But we believe that OLSR periodically shuts off some flows. So some high-performing flows get shut off, so other flows get to go forth. So this improves fairness. Bitrate control slightly degrades performance. By turning on wireless bitrate control, you do this search for bitrates, and you end up choosing a lower bitrate. And this again shows you an example of an interaction between bitrate control and TCP rate control. So the means of TCP now go below. So the 2 points on the left are with bitrate turned on. The 2 points higher up are without bitrate, but with or without OLSR. And hop is the red line as before. The benefits with all of these turned on is less. It's about 4x in median and in 13x for the lower quartile.
But if the routes are changing, then, and if you have a buffer packed on one path and your path changes, you won't have the benefit of the virtual retransmission.
Only you'll have the benefit only on the part of the route that's common, and so the numbers you see here are inclusive of those effects. So here in B, bitrate control doesn't help much, but in G, bitrate control helps because G has a much wider range of bitrates to choose from. And so the purple line is the one TCP with bitrate. This is default TCP, and that's hop set to a fixed bitrate, actually the maximum bitrate. So hop doesn't get the benefit of bitrate. It's just set to the maximum bitrate in this experiment. And the benefits are less compared to what we saw before, the median and lower quartile benefits. The reason why we didn't actually experiment with hop with bitrate control turned on is because bitrate control depends on acknowledgements, and hop doesn't use acknowledgements. So we need to devise, and this is one of the the next things to do to devise a bitrate control scheme that can actually benefit from Hop's design. And I will give you. Should I stop?
Let's say 5 more minutes or something.
Okay. So one of the reasons, let me skip over related work. There's nothing here to say except all of the ideas are bread and butter ideas that people know about. We just put them together into a package that performs performs significantly better. So the reason I'm interested in this, like I said before, is to look at this extreme point in this design space, which is DTNs, where there's a high level of mobility. Then come back and then design a network protocol stack that gives you high performance and maintains robustness of the performance across a variety of different environments. So WLANs and meshes at one end of the spectrum and DTNs on the other end of the spectrum, and all points in between. Right? Why may you want something like this? I don't know. This is a thought experiment where you have a town mesh network. Let's call this town Amherst. You have a network of buses. Let's call this DieselNet. And then you have a sensor network deployed along a river where a bus that's close to a bus stop, and the buses have 802.11 and even 3G on them. This is along the Fort River. And you may just want to hook up all of these to one of the goals of the DieselNet deployment and the town mesh deployment is to save bills for monitoring town equipment. So instead of using something like 3G, you can save a lot of individual phone bills by using a network like this. If you could just put them all together. But how do you put them all together if in this environment you have a whole range of protocols, ETX, ETT, EDR, WCETT, RTT, hop count. In MANE environments, you have geographic, just do a Wikipedia search and it will give you 100 different routing protocols for MANEs. Do the same for DTNs, it will give you tens of protocols for DTNs. How do you maintain this network? Yes?
That's a good question here. People have been, all of us actually, have been doing multi-hop wireless networks for a long time now. And apart from these specialized situations like SensorNet, we really haven't seen any deployments. We're actually now withstanding what they've never done. So how much of what you've done here applies to single hop wireless, which is the most common situation here?
So the benefits that I showed for the single hop experiments, it's about 2x to 2.5x benefit. That's the benefit you can expect over WLANs. There are some optimizations that blocks allow for in terms of how to do bitrate control better. That's a single hop benefit. But the most important, the biggest numbers come for multi-hopper. So mesh-like environments, which are seeing increasing levels of deployment. It's anyone's guess if this will keep growing or not. And DTNs, I believe that from a research perspective, it's useful to look at this extreme point in design space. And an example of why it's useful is Hop. I mean, the design of Hop is a DTN protocol. It's a better DTN 2.5, if you will. Except it also gives you significant performance improvements over WLANs and meshes. That's a reason to look at it from a research perspective, even if DTNs never see the light of day.
I agree. You should look at the extreme design one. I was just wondering.
So the other thing, Jitu, I want to point out is I think the Amherst town mesh, a lot of people are using it and it is over multi-hop. It's not a single hop.
So to give you some idea of the numbers, I mean, there's some 40 buses. If you had to monitor like 50 different town equipment things, and you have a 3G card for each of them, you're paying $50 a month. $50 a month for 40 to 50 devices adds up to about $25,000, $30,000 a year. Setting up a mesh network is a one-time expenditure of a few $1,000s. So there are applications for which even today there's value. How far they'll go is anyone's guess. It depends on how the technologies evolve.
That comparison is not quite fair, right? Because if you get 3G coverage in a much wider area than you would get mesh coverage. And if you started expanding your mesh to the same area in which you get 3G coverage, your costs would escalate rapidly. I don't know what the break-even point would be, but
bear in mind, most of the data actually is generated in an urban core. So it's not, the argument's not you do away with 3G. The argument is like reducing per byte cost. Right?
So to answer Jitu's question, I will not argue in favor of mesh networks or even Wi-Fi access, single hop Wi-Fi access points over 3G. In fact, I don't think that's the argument to make here. there is value to looking at how these two can coexist. There are problems with 3G. 3G is not the solution, and we are looking at some of these problems too. And we find, and some of this work is in collaboration with Ratul as well, Wi-Fi can augment 3G in a useful way, in a practically useful way. So I'll skip over some of the research challenges to realize this vision of a network protocol stack that works across environments, and I will go to just bitrate control, like I said. So there is an interaction going on between transport level rate control, like in TCP, and bitrate control at a lower level, right? And this is a negative interaction. As we can see in experiments, in B it hurts, in G it helps, and we don't know what will happen in N. It seems like bitrate control will be useful as opposed to not having bitrate control. But this is the problem. Let's look at what is the problem bitrate control is trying to solve ideally. You're trying to find a modulation rate R that maximizes R times 1 minus loss rate achieved for that R. That's the problem you're trying to solve. But if you have ARQ in the system, whose overhead is significant, you want to keep the loss rate low because at high loss rates, ARQ overhead catches up. So the space of rates you explore is lowered. If you have TCP on top of this, you really want to keep loss rates low. So the space of rates you can explore is lower. This is an example of an interaction. So ideally what you could do with bitrate control is now impacted by inefficiencies introduced or constraints placed by ARQ and TCP. And so doing away, optimizing for these two, ARQ and rate control overhead, like blocks do, is an opportunity for doing better bitrate control, which is work in progress. It can also help detect interference versus channel losses. So that's a normal block, like you guys pointed out in the beginning. You can have these frames much smaller and get all the benefit of having small frames or the exponential reduction in bit corruption. So think of each fragment or frame here as just something that's associated with a CRC or some kind of a error detection entity, error detection mechanism. Once you go to this, once you go to the smallest possible frame size, then there's no benefit to going to smaller frame size. Now you have to pick the best rate that's possible. And the best bit rate that works for you, wireless bit rate that works for you, and that itself is a hard problem, and it's a well-known problem of distinguishing interference versus channel losses. You want to adapt bit rates to channel losses, not adapt to interference losses. If you go down to small fragments inside a block, none of the protocol above changes. You get all the higher level network layer, transport layer benefits, but you have these kinds of benefits. You can look at the pattern of corruptions. So the dark ones are the corrupted frames, the light ones are the non-corrupted frames, and you can distinguish between interference and loss, and you can use this in your bitrate selection algorithm. All these kinds of things come free in Hop. Not new ideas again, but when put inside this package of blocks, they fit in well into a stack that can give you benefits both in single hop networks as well as multi-hop, mesh, DTN, MANI-like environments. So I'll conclude with that. I put this because a bunch of people here are working on white space stuff, but Hop's source code is available at hop.cs.umass.edu. I welcome you to use it. Please download it. Any transport or any optimizations you come up with for transport, compare against this. We are trying to make this as usable as we can.
Thank you.